Thanks. So out of the 6,000 exoplanets that we have discovered so far, only about 200 or so have any spectral information. And these are, of course, the image planets and the transiting planets. And it is for this subset of exoplanets for which detailed characterization is possible. So for the imaging side of things, this field, I think, has been doing a lot of atmospheric studies over the last decade or so. And we have found some interesting emerging trends. So first of all, Keelan Hawk in 2023 showed that directly imaged planets almost all have solar C to O ratios. So there's not really much going on in C to O ratio. Using KPIC, I looked at a sample of planetary mass companions from 10 to 30 Jupiter masses and found that they also have C over H, which is a tracer of metallicity here, consistent with solar. And the stars that these companions orbit also have solar metallicities, suggesting a broad picture of chemical homogeneity. And so it's clear that in C to O, it's somewhat limited to what we can do. And there's also an aspect here of from the ground, there's only so much we can do right now with current instruments in terms of looking at the coldest and most challenging planets. And the atmospheric field has now recognized the need to go beyond C to O, so we can, with high enough SNR data, look at things like isotopes, nitrogen, and these refractory elements. And refractory elements in this context are things like iron, silicate, and sulfur, which are things that tend to stay in the solid phase of the protoplanetary disk. So in this context, sulfur was recently recognized as a refractory element because beyond about 1 AU or so, it is locked in the disk solids. So this makes sulfur and these other elements really excellent tracers for solid accretion. And of course, a gas giant, when it forms, it accretes a combination of gas and solids, but that exact balance is unknown from both theory and observations. So here, I'm going to mostly be focusing on HRs of 99, which needs no introduction. I really like this nice movie made by William Thompson recently. And this is a really excellent system and a unique system to study planet formation because we can actually compare the compositions between 4 gas giants that have roughly similar masses. So there's 2 papers coming out for this system based on JWST near-spec observations. And the first paper is coming out in Nature Astronomy in a few weeks. And in this paper, we used a first set of observations, looked at 3 of the 4 planets, and we got the first H2S detection. In the second paper, which represents an update to this work, we also have planet B. And because the SNR and the integration times were higher, we have more sulfur detections. And so this is what I'm going to be focusing on today. And so as Alex already mentioned, JWST is transformative for high contrast spectroscopy. So on the left here is the processed data cubes, which are just dominated by the star. But once you use the spectral difference between star and planet at R of a few thousand to subtract out the star and model it out, you can get these really excellent detections of the planets. And the significance of some of these planets are detected at up to 200 sigma. So again, I refer to JB's talk on Tuesday for more of the technical details. Just to prime you a little bit for the JWST spectra, this is kind of the data we were getting before JWST, predominantly low-resolution spectroscopy and photometry. And it's probably true that many of you here have worked on some subset of this data. More recently, 5 years ago, we had the first high-resolution detections of these HRs of 99 planets. And here the data are in black, and they're modeled with a joint model considering the star and the planet. And here the data quality is really good and allows us to measure the spins of the planets and their radial velocities. But overall, we're limited to about a 15 sigma detection of each planet. So now with JWST, we see each individual molecule to above 10 sigma. So I'm going to walk you through this. This is the first panel of G395H. So you see the water lines, and then the methane band, and then at the edge of this, you see the H2S lines. I'm just showing an example for planet C, but of course in the system we have all 4 planets. The data and model are hard to distinguish, but the data here is in black, and the model is an atmospheric retrieval model that I made using petite radtrans. And because of the high quality of the data, this required almost 2 years of iterating and making sure we're getting the most robust results possible. So moving on, we also have CO2, which is basically impossible to get from the ground because of telluric CO2. And if you go redwards, you enter the forest of CO lines, where besides the main isotope log of CO, you also see C18O and C13CO and C18O. So this is, again, in its full glory, the spectra of HR799c. Planet B is actually a little bit colder and less massive than its 3 neighbors. So for this planet, we also have a 5 sigma or so detection of ammonia, which allows us to measure a 4th elemental abundance, that of nitrogen. And so this is the result, putting all of this together and all of these 2 years of efforts together in one plot. So to first order, we can see that the HR799 planets are definitely metal-rich to a similar extent as Jupiter and Saturn. And you can also contrast them with these brown dwarfs, which are the 10 to 30 Jupiter mass planetary mass companions that I mentioned in the beginning. And so we are definitely seeing a distinction there. There's also some interesting trends that I'm going to get into. But first of all, the enrichment in sulfur of these planets implies that they accreted a lot of solids. Now, these solids can be both small pebbles or large planetesimals. That is hard to constrain. But if we make some simplifying assumptions, we can use the sulfur abundance to estimate the accreted mass in solids for each planet. So this was calculation done by Yayati Chachan, a postdoc at UC Santa Cruz, who's done an amazing job on the modeling side of this effort. And he's calculated that the 4 planets have between about 50 to 90 Earth masses of solids. And I'm just focusing on planets D, C, and B, for which we have the solid detection of sulfur. And so these are indicated in the filled symbols here. And if you overlay the classic predictions from pebble accretion or planetesimal accretion, then these solid masses we're finding are actually pretty consistent with them. So both pebble and planetesimal accretion in this sense can work. And in the bigger picture, this means that these planets may not be as weird as they might have seemed to be, and they might be explained by the same physics that we're using in other planetary systems. And of course, there's these interesting trends that one of the earlier plots sort of hinted at. So here, I'm showing these trends more clearly. And so this is plotting the ratios between different metals. In C to O, there's not much going on. All of them are pretty close to 1. But there's these interesting and tentative trends in the volatile to refractory ratios. So if we look at planet B first, which is the brown point, it is uniform in C, O, and S, but it seems to have a high nitrogen abundance at the 2 sigma level. On the other hand, the inner 3 planets have a higher amount of carbon and oxygen than sulfur. So what does this mean? We need to place this in the context of the disk and the formation of these planets. So here I'm plotting the locations of the 4 planets at their current day orbits and estimates for the CO and the N2 snowline locations when these planets were forming. So it turns out that modulo some migration, planet B likely formed outside the CO snowline. And so if this is the case, then C and O have condensed out into solids. That is what the CO snowline is doing. And so this means that this planet would accrete carbon, oxygen, and sulfur in equal proportions. However, if it formed inside the N2 snowline, then N2 gas evaporates there and is a known mechanism to enrich planets in heavy elements. So if that's the case, then that might explain the high nitrogen abundance of planet B. On the other hand, the inner 3 planets, they actually can be explained by a similar picture. So here, it's the CO snowline that's relevant. And if these planets formed inside the CO snowline, they have access to the CO-rich gas that could increase their carbon and oxygen abundance beyond their sulfur abundance. And so while I describe this as a qualitative picture, Yayati has actually done the calculations to show that this works in a quantitative sense as well. So because I don't have much more time, I'm just going to quickly advertise some other programs that me and my team are working on. So I'm going to talk a little bit about AF Lep, and I'm also really excited about EPSINDI AB, for which we're getting basically medium resolution spectroscopy from all the way from 3 to 20 microns. And you can even see the Airy rings in that detection map there. So this technique works for a wide range of planets, both close in and extremely low temperature. And there's a variety of talks and posters at this conference about it. So for AF Lep B, we achieved 80 sigma detection of a planet at 0.3 arc seconds, proving that NIRSpec is indeed working better than most other instrument modes, both from the ground and JWST at these really small separations. And of course, with NIRSpec, you get the spectrum. So we have H2S detection for AF Lep B as well. And preliminary results show that this planet is also nearly uniformly enriched in C, O, and S. And because it's at 9 AU, we're going to be working on explaining how it might have got that enrichment pattern at its current distance. For EPSINDI B, I'm just going to also advertise Anikit's poster, and these are question marks, so do check out his poster to look at the actual data. So with that, I'd like to thank you and take any questions.
I'm curious, if we were to find a directly imaged planet in a system that also has a transiting planet, could we do this sort of work that you're showing for HR 8799 between the transit method and the direct imaging method, or is that a totally different game?
Do you mean applying the same techniques or the same like atmospheric modeling? Like the data reduction or the?
I guess I'm curious about like the test for like core accretion, or if that test would vary a lot from what you're.
Yeah, I mean, if we had such a system, which I think there are some imaged companions where there's inner RV planet candidates. But if there was a system where we can get transmission spectroscopy of like a hot Jupiter inside and some distant giant outside, then that would be really interesting. But I think broadly, it is still interesting to compare the abundance patterns we're seeing for distant giants to what the transiting community are finding, even if they're not in the same system.
So you've got the ultimate data set on HR 799. What is there left to do on this system?
Yeah, that's a good question. So I think there is still potential for longer wavelengths, so in Miri wavelength, which are sensitive to ammonia. So we don't have ammonia detection for planets C, D, or E. And if we can get that, then that would test this picture that I've presented here. So longer wavelength data would be my go-to. And that would also be more sensitive to the clouds if we can get the continuum.